This is how the system works. You have a laser system. You irradiate a remote sample. In this particular case, we are looking at soil which was contaminated with explosives which were tested there. You look at whatever signal that comes back at you, collect it with a telescope, and analyze it as a function of the wavelength. This is for TNT residue in soil at 150 meters. Blue curve is the reference curve as one would measure in the laboratory, and red curve is what is obtained, the signal that we see coming back from a sample as a function of these CO2 laser wavelengths. As I mentioned to you, CO2 laser operates on discrete lines, so we get only discrete points. Nonetheless, you can see that there is very close resemblance. More important is to look at the lower curve, which is the same similar sample but obtained from local gardening store, which we know does not have any, hopefully doesn't have any TNT residue. And what you see is a completely flat structure, indicating that what we are measuring is in fact TNT. And the next slide shows you how the detection capability varies as a distance. It should go as distance square, which is what you see. And what we see here is that even at a distance of 150 meters, we got substantial amount of signal left, fairly good signal to noise ratio. And the question that is often asked, why did you go to longer distances? Well, if you are at China Lake, which is a desert in Southern California, which is where you are allowed to look at this kind of stuff, propagate laser light over long distances. It's a Navy facility. If you are trying to propagate laser light horizontally, you need adaptive optics for longer distances, because what you see is that there is substantial movement of the beam because of the thermal variations along the beam path. And we did not have, in this particular case, adaptive optics, but we could have gone to distances probably of the order of half a kilometer. You can also use the same technology for measuring gas cloud. If there were a release of chemical warfare agent at some distance, you want to know before you get there. And so we carried out similar measurements. A gas cloud, in our case, was contained inside a tube. The gas that we used was SF6 because it is relatively innocuous gas, and you're allowed to release it in the atmosphere. Same kind of system. You see measurements shown on this slide. Blue curve is what your laboratory measurements would be, and red curve is what we get using the remote measurement. This is at a distance of 200 meters. So the sample is sitting at 200 meters. We are interrogating it from that distance, and we are able to see the presence of SF6 in that system. And similar distance dependence here, because of the fact that the sample is large, we had a tube roughly 2 meters diameter, so beam wander really doesn't hurt a lot, and we are able to go to roughly 400 meters for this measurement. What this allows us to do is to put an upper limit on what we can, or lower limit on what we can measure. We can measure 1 ppm meter, a gas cloud at a concentration of 1 ppm, length 1 meter. What I forgot to mention on the previous slide is that from the previous slide, we also get a measurement capability of roughly 10 micrograms per square centimeter at a distance of 50 meters. 10 micrograms is less than a fingerprint. So you can see the level of the sensitivity that is capable, that you are able to achieve. As I mentioned, again, CO2 lasers are heavy. What you want to do is to use quantum cascade lasers because they are light, low power, so all this size, weight, and power advantages. Again, the same kind of multiple laser system that I had mentioned earlier, because you need to tune over a broad range. You combine the 4 beams, send it off to a target, have a small telescope that looks at what comes back and analyzes it. Laser system is the same that I had shown earlier, and the whole entire system looks as shown here. The laser package is here. This is a small telescope. Laser output from this telescope, from the laser, goes into the telescope, directed by a 45-degree mirror, goes to the target. Whatever comes back from the target is collected by a 4-inch mirror at the back and is analyzed. This system has been tested for detection of multiple explosives. It's tunable from 7 to 10 micrometers. It's very light, as you see. one person can carry it, weighs less than 20 pounds. And it is capable of detecting most of the military, commercial, and homemade explosives. Also chemical warfare agents, but it has not been tested for chemical warfare agents yet. So, I'm coming to the end of my presentation. I've told you, given to you where we stand in terms of performance, all the different applications where quantum cascade lasers have become important and are being very rapidly being deployed. Directional infrared countermeasures, testing IRCM systems, target illumination, target designation, beacons, chemical warfare agent explosive detection, and medical and environmental testing, which I didn't say much about, but when you recognize that it is possible to measure all kinds of gases, all kinds of impurities at very low levels, it immediately tells you what else one can do with this kind of source. There are two areas which have not been explored so far. One is free space optical communications and LiDAR, and that will also eventually will happen. One cannot complete a talk like this without at least giving some idea as to where things are going to go. One of the things that has happened, and as we all know, when you provide 1 watt of power level, the question comes back, why not 2? We need 2, why not 4? So now that we have 4, the question is, why not 10 watts out of a single element system? The number that I quoted you, 4 watts at 4.6 microns, is from a single emitter. People would like to have 10 watts out of a single emitter because then you can combine them, polarization, combine them to get 20 watts. So what I see is in the next year or year and a half, perhaps we should be able to reach 10 watts of power level. The problem is not going to be whether we can or we cannot. The problem is going to be how are we going to carry out the difficult task of thermal management. But that part has already been addressed by near-infrared people who have produced lasers that produce kilowatts of power. So clearly, there is a technology of thermal management. One of the next thing is, why not multiplex several QCLs, not just 2, but several QCLs to reach even much higher power levels with high beam quality. My favorite thing that I like to say is that what I would like to do is to get QCLs to a power level where they will replace CO2 lasers in all low power the applications, which are many. Low power applications include marking on physical objects, a very large application. Many companies make tens of thousands of these lasers each year. Why not use quantum cascade lasers? There is size, weight and power advantage. We are off by a factor of maybe 2, maybe a factor of 3 in power level. But that will be my fondest dream to replace CO2 lasers, because I think having invented CO2 lasers, if I do something to replace them, that's not a bad thing to do. And finally, there are a whole lot of non-defense applications. I haven't touched on any of them, but these include medicine, food safety, public health, free space communications, and so on. Just as an aside, many of you probably know, we also make a system for analyzing human breath for non-invasive medical diagnostics. Clearly, quantum cascade lasers would be ideally suited for that kind of application. And I look forward to days, next year, 2 years, 3 years, where I can stand up again and say, yes, all other things that we have predicted have come true. Ladies and gentlemen, thank you very much for your patience.